So good evening, I'm Pramod Gawal, TA of this course. So I'm going to take a problem solving session 8 on the mass transfer operation 2 on the chapter membrane separation technology. So moving ahead, so here is a brief recap. Fundamentals of membrane separation process, then manufacturing membrane, then advantage of membrane separation processes, limitation approaches to improve various models and application design aspects. So I think all of you have gone through the week 8 lecture which are available on SIM portal. So based on that, I am going to take problems like, including MCQ and numericals. So starting from the MCQ, the question number 1, ultrafiltration. Membrane. Ultrafiltration membrane has a pore size range of, right? So here is the option given. A given less than 2 nanometers, B 0.1 10 micrometers, C 1 to 100 nanometers, D 0.5 to 10 nanometers. So less than 2 nanometers, this is size for the reverse osmosis RO, and 0.1 to 10 micrometer for the microfiltration, 1 to 10 ultrafiltration, and option D, this is the size for the nanofiltration. So in this question, ask the size of the ultrafiltration membrane. So option C is correct. Moving to the question number 2, microfiltration membrane has a operating pressure range of. So option givens. So 2 to 4 atm for the pressure range microfiltrations, and 5 to 8 ultrafiltration, and 10 to 25 nanofiltration, and 25 to 40 atm for the RO. So in this question, ask the microfiltrations. So option is a correct. So moving to the question number 3, which of the following separation mechanisms of a reverse osmosis? So here is a separation mechanism asked for the reverse osmosis. So option A is a sieving or size exclusion. So this mechanism for the ultra filtration and microfiltration. Yep, and microfiltration, right? Solution divisions. So this mechanism, this is a separation mechanism for the reverse osmosis. And sorption diffusion, this is for the gas separation. So in this question, ask the for the separation mechanism for a reverse osmosis. So option B is the correct solution, diffusion. Now moving to the question number 4, which of the following membrane processes are in order to descending order, like size? Right. So our size microfiltration, then ultrafiltration, then ENDF, and this is R. Oh, right. So this is the descending orders. So check the options. The C is correct one. Now moving to the question number 5. If the pressure drop is delta P is 1000 units, the flux J is a 40 units. What is the hydraulic membrane permeability? Right. So to calculate this hydraulic membrane permeability, so based on the Darcy law, right? JW, which is a flux P into delta P, right? So LP is a permeability into delta P, right? So LP is equal to JW divided by delta P, right? So JW given 40 and delta the pressure drop is 1000 unit. So 40 by 1000, right? 0.04. So permeability is a 0.04. Check the option. So B is a correct. Moving to the question number 6. Question number 6. Here are the three concentration figure for the ultrafiltration of the solution of macromolecules. Bulk concentration 1.5%, permeate concentration 0.32%, concentration at the membrane surface 8%. What is the rejection coefficient? Right? It is a CP, right? This is a CP. So CP is a solute concentration in a permeate, right? And this is a CB, the solute concentration in the bulk solution. And concentration at a membrane surface is a CM, right? So to calculate the rejection coefficient, R dash equal to 1 minus Cp by Cm. Right. So 1, here is a Cp 0.32 divided by 8, 0.96 of the rejection coefficient of the protein. So check the option C is the correct one. So question number 7, the following concentration figure are given for a reverse osmosis of salt solution. Cb 4%, Cp 0.03%, Cw 8%. What is the polarization modulus? Right. Cm, right? Cm, this is a Cm, right? To calculate the polarization modulus, here is a formula. M is equal to Cm divided by Cb equal to 8 by 4. This is a 2. Option is a correct. Into the question number 8, ultrafiltration membrane offers a steady state solvent flux of 0.052 meter cube per meter square per second under the gel polarization. The applied pressure drop is a 4 bar and the resistance offered by the membrane is a 2.4 into 10 to the power 9 meter inverse. What is the resistance offered by the gel layers? The viscosity of water may be taken as a 0.9 centipoise, right? So Cp convert into the Newton. Okay, Newton into second per meter square. Like JW is equal to delta P viscosity into Rm. Here is a two resistors by resistance offered by the membrane and the resistance offered by the gel layer, Rm and Rg, right? So take Rm plus is equal to delta P by U into J W, right? So viscosity given, then flux given, and pressure drop given, right? 4 here convert into the Newton per meter square, means pascals. 4 into 10 to the power 5 divided by 0.052 into 9 into 10 to the power minus 4, right? 1 over 9 to 10 to the power minus 4 Newton s meter square, right? Or kg meters equal to 8.54 into 10 to the power 9 meter inverse, right? So here is a Rm given 2.4 10 to the power minus 10 to the power 9. So Rg is equal to 8.54 minus 2.4, same units, I so 10 to the power 9, right? So 6.14 into 10 to the power 9 meter inverse. So here is a resistance offered by the gel layers. Check the options. Option A is correct. Moving to the question number 9, the limiting flux through ultrafiltration membrane is 0.042 meter cube per meter square per hour, and the membrane surface mass transfer coefficient is estimated as of 5 into 10 to the power minus 6 meter per second. If the membrane rejects the solute completely, the polarization modulus. To calculate the polarization modulus, denoted by the em to Cm by Cb, right? Here is a Cm is a solute concentration in the liquid at the membrane surface, and Cb is a solute concentration in the bulk solution. So which is equal to exponential flux divided by mass transfer coefficient K L, right? So here is the flux given and also mass transfer coefficient given. Put the value in these equations. 0.042 into okay, here is the hours, so we have to convert into the seconds. So pi into 10 to the power minus 6 into this 100. So after solving 10.31, check the option. So option B is matching. No. Move to the question number 10. In a spiral wound ultrafiltration module, Model for the protein separation, the bulk concentration on a feed side is known to be 2 mass percent, and the apparent rejection coefficient is 0.975. The flux 1.8 10 to the power minus 5 meter cube per meter square per second, and the feed side mass transfer coefficient is 4.4 into 10 to the power minus 5 meter per second. So what is the true rejection coefficient? So in this question, the bulk concentration given, that is the CB, right? CB. So here is the two cases. First case, CB given 0.02 mass per, right? Then apparent rejection coefficient equal to 1 minus Cp by Cb, right? Equal to 0.975, right? So here is a Cb. You put in this equation here Cb. So we will get the Cp 5 into 10 to the power minus 4, right? Here is Morton's case. So now JW Cp minus Cp equal to KL by Cm minus Cb. So JW given 1.8 or 0.02 minus Cp is 5.10 to the power minus 4. KL value given 4.4. Right. Cm minus 0.02, right? So calculate the Cm. So you will get 0.1 after calculating. Now we have to calculate the two rejection coefficient. One minus Cp by Cm, right? So 1 minus 5 into 10 to the power minus 4 divided by 0.1. 0.995. So this is a true rejection coefficient. Question number 11. A 75 micrometer thick polysulfone membrane has an average porosity of 0.35. Pure water flux through the membrane is 25 meter cube per meter square at the pressure drop 1.2 bar at 25 degrees Celsius. The average pore size is estimated to be 1 micrometers. Calculate the tortuosity torsaticity factor of pores and resistance to the flow offered by the membrane and its permeability. The viscosity of water at 25 degrees Celsius is 0.9 centipoise. So here you have to calculate the torsaticity factors, then resistance to flow offered by the membrane and its permeability, right? So here Lm given 75 micrometer. Membrane thickness, right? Convert into meters, 75 into 10 to the power minus 6 meter, right? Then membrane porosity, average porosity, which is epsilon 0.35, right? Delta P is a 1.2 bar. Convert into the Pascal. So 1.2 into 10 to the power 5 Pascal or Newton per meter square. Viscosity 0.9 cp. So it's a 9 to 10 to the power 10 to the power minus 4 Newton into meter square. And JW (25) divided by here is hours, converted to the second. So 6.94 into 10 to the power minus 3 meter cube per meter square into second. So here is the formula GW equal to 32 mu. This is a torsion factor, right? Tau into delta P divided by membrane thickness. So here you have to calculate this quantity. First, the torsion factor. So all the value given, put in these equations. 0.35 into 10 to the power minus 6 square, 32 into 9 into 10 to the power minus 4. So this we have to calculate into delta P 1.2 into 10 to the power 5 divided by 75 into 10 to the power minus 6, right? So now JW given, sorry, given the convert into seconds, so it's 6.94 into 10 to the power minus 3, right? So all the just we have to calculate this one torsion factor. It's a 2.8, right? Now torsion factor calculated. Now resistance to flow offered by the membrane, right? So based on the Darcy law, JW is equal to delta P mu R M. So you have to calculate. So all the quantity given, so you have to calculate the RM. So RM equal to delta P mu into JW. So 6.94 into 10 to the power minus 3 divided by 1.25. Sorry, 9 into 10 to the power minus 4 into 6.94 into 10 to the power minus 3. So it will get 1.92 into 10 to the power 10 meter inverse. So this is the resistance to flow upward by the membrane. Now next task is we have to calculate the permeability. So to calculate the permeability, so JW is equal to LP to delta P, right? So LP to JW, so delta P, right? So 6.94 to 10 to the power minus 3, 1.2 to 10 to the power 5. So 5.97 into 10 to the power minus 8 meter cube per meter square into second into Pascal. So this is the permeability. Now laminar flow through the pores has been assumed in the above calculation. So this may be easily established by the calculating the Reynolds number. So Reynolds number is equal to du mu t. Okay. So here is a take velocity 2536 meter per second and density 998 of water, density of water. So put in these equations. 1 d is 10 minus 6 into 6.94 to 10 to the power minus 3 into density 998 divided by viscosity 9 into 10 to the power minus 4. So 7.73 into 10 to the power minus 3. So flow is a laminar. Moving to the question number 12. Macramalucular solute is ultra filtered using the polycarbonate membrane at 25 degrees Celsius. The solution concentration is 0.015 molar. Let's see, that's CB. So, and 96% solute rejection is achieved if the feed side pressure is a 4 bar and downstream pressure is a 1.5 bar absolutely. Calculate the following if the concentration polarization modulus is. Okay, calculate the effective 1 minute for a bar. So calculate, here is a missing. Calculate the effective pressure driving force. Here is a missing in this question. So neglect the concentration polarization, then calculate the same if the concentration polarization module is 5.5. So here calculate the effective pressure driving force, right? Neglect the concentration polarization and calculate the same if concentration polarization module is a 5.5. So okay, here two cases. So R dash is 0.96, right? No concentration polarization. Yes. So Cm is equal to Cb. It's a 0.15 molar, right? So Cp is a 0.015 minus 1 minus 0.96, right? So Cp is a 6 into 10 to the power minus 4 molar. Now effective osmotic pressure. Denoted by delta pi equal to R into gas constant into delta C, right? So here is a 0.0821. So unit is a atm, so convert to a bar, multiply 1.013. Temperature is a 298 Kelvin. Convert into 25 degrees Celsius to the Kelvin into 0. Cm Cp minus Cp, right? So it's a 0.356 bar, right? Now here is the delta P, pit side pressure and the downside pressures. It's a 2.9 bar. Now we have to calculate the effective pressure driving force. Effective pressure driving force equal to delta P minus delta pi. So delta P is a 2.9 minus 0.356 to 2.543 bar. So this is the effective pressure driving force for the first case. Now in second case, if the concentration polarization modulus is a 5.5, so then we have to calculate the effective pressure driving force. In a second case, right. So M is equal to Cm by Cb equal to 5.5, right? So Cm equal to 5.5 into CB 0.15. It's a 0.0855 molar, right? And CP 0.085855. 825, right? 825 minus 0.96 equal to 0.0033 molar, right? Now delta effective osmotic pressure delta pi is equal to RT delta C, right? So 0.0821 to 1.013 into 298 into this one cm 0.0825 minus 0.0033, right? 1.963 bar. Now we have to calculate effective pressure driving force. To delta P minus delta pi at 2.9 minus 1.963, so 0.937. So effective pressure driving force is a 0.937 when the concentration polarization majority is a 5.5. So I cover all the question based on the these topics. So thank you all. So we will meet on next Friday on same chapter on next next topic. Thank you.